Now coming to sessions on integration would be essentially simple. You have done high school integration. So, we are going to talk about integration. This is just to recollect or remind you what you have learned. This is not really to teach you something new. And in the next class, we will talk about integration by parts, maybe about also a little bit about how to handle rational functions. So, these are the things which you have learned in high school, but we are just recollecting so that you can keep in mind, because you have to start doing some integration gradually as you go on, and then go to the real stuff which is called Riemann integration. Here we are only talking about continuous functions over a given domain, and you are talking about functions which are continuous over their domain, and we are essentially trying to talk about integration of that, which is in case of definite integral nothing but we are talking about area under the given curve. But also we have to know what is antiderivative in order to do that, because that is what the fundamental theorem of calculus shows us. That is what we have learned in the last class. If I just go back and see what was there. So, you have a look at what there, and you can immediately see what we have essentially tried to do, that this integration, this fb minus that integral a to b is fb minus fa. So, this is something very important, that is integral a to b f t dt is f of b minus f of a, where f is the antiderivative of small f, capital F is the antiderivative of small f. So, here we will just recollect some well known integrals. Okay, let us do something which is very standard, and so this is just, so you must be wondering where the sign dx comes from. We will start explaining that, but let us write down which you have possibly known, have not bothered much about understanding and walked through. I think this is very simple, this is the antiderivative, you know. So, you know a lot about derivatives, so you can do this. For example, this particular derivative dx by 1 plus x square is, this is something which is used very much in actual applications. Of course, I am just writing on the side. There was a famous mathematician who made this comment that when I was a young man, all of my friends shied for luxury, but I only shied for a knowledge of the calculus. So, knowledge of the calculus is very much underpinning of an scientifically educated person. So, now this is something very important, tan inverse x, and also remember tan inverse x, when I told you these are really not functions, but multifunctions or set valued maps, and but here we are only talking about the principal value. Please remember this fact. And this is also an important thing. These are very much used in engineering. Now, I have two things to write, and then I have another thing to write. ln means log natural. Ln of x actually also can be written alternatively as log e of x, is the natural logarithm, where the base is the number e, which lies between 3 and 2, and e is equal to 2.7178. So, this is an irrational number, by the way. The way you have proved, one can say that pi is an irrational number, e is an irrational number, means e to the power r for any r rational is a irrational number. There are a lot of interesting facts and deep facts associated with calculus which cannot be done in such a basic course. So, we will really focus on these two things for the next part of the lecture. So, what do you mean by integral dx, and why do we write that this is x plus c? The idea is very simple. Observe first that what does dx mean. In your mind intuitively you can think that dx is very small little parts of x, and we are now basically you take x some object and you have broken it into small parts, and each of those parts you are calling dx as if you, like everything is made of atoms, like, and if you have all the atoms of a say a solid body and you can pull them inside, you get the body itself. So it is exactly the same idea intuitively of physical, it is a physical intuition that you are dividing x into small parts, and then that those things are actually joined together to form x, and c is of course the constant of integration which you have to say that okay, how do you physically explain it, that okay fine, now you are trying to join because you have broken. Now suppose you have torn a paper into small pieces, a page of a book, and now I want to tell you okay bring them up together by pasting the correct portions, but even if you bring them there will be some little part which will be inconsistent, it cannot be exactly the same thing. So it is x plus c, if you can make it exactly the same thing then c is 0, if you are not the same thing then c is something. But what dx actually is, so now dx is not the numerator of dx of f, dx is something is called the differential. And how did this terminology of differential originate? You see a lot of these thought processes came from the physical sciences, it came from mechanics, and as a result of which you know lot of these thought processes are very intuitive, very dependent on physical intuition. So for example here when I am talking about dx, what I am actually meaning is the following. Now you know if I go by Taylor's expansion of a function at x plus h when h is very small, then I can write it as f of x, I just want to make a first order expansion, h. So this is a Taylor's expansion, Taylor's polynomial which we have already studied, where c is some quantity lying between x plus h and x minus h. I am assuming h positive for the time, it does not matter, you could take h negative then it is opposite. So what is the whole issue here? Now this is something which is an error, it is actually an error term. Now so effectively when h is very small, I can write this as, that is when the distance between x and x plus h is very small, I call that, I say that the value of the tangent line and the value of the function are very near, they are almost the same. Physicists have a habit of writing h as delta x. So what we can write is f of x plus delta x minus of f x is almost same as the derivative f dash x into delta x. So this was a symbolism of the infinite sort of something called infinitesimal, and people were using that, but do not get bogged into all these things. Let us just look into this very simply. What does it mean? Now as delta x becomes smaller and smaller, this approximation becomes better and better. Now this one, this distance between the difference between the function value at x plus delta x and the function value at x is often symbolized by physicists as delta y. This delta symbol is also very important in numerical analysis. On the older version of numerical analysis or old numerical analysis books in mathematics has this sort of symbolism. Okay, but this symbolism is useful. So it tells you, so this, the change in the dependent variable is nothing but the derivative, this is your ddx of f, or this is your dy dx basically, into change in the dependent variable. So change in the dependent variable is the derivative into the change in the independent variable. So this is called a change in the dependent variable is equal to derivative into change in the independent variable. Just look at this quantity. Just look at this quantity f dash x into delta x. This quantity, when delta x is very small, we call the above quantity as a differential y, differential of the function df or dy, whichever one. So, we write dy is equal to f dash x into delta x. Now, an interesting thing emerges. Now, let me consider the function y is equal to f x is equal to x. Then instead dy is basically my dx or df. So, what it would mean? So, dy in this case or dx is equal to f dash x is just 1 into delta x. So, delta x, whatever be your x, it can always be written as d of x. So, that is why we can say the differential of y. So, delta x essentially is then called the differential of x. That is why the differential of y essentially telling the change of y when y is the change is change in x, change in y when the change in x is very small is nothing but the derivative of f at x into the differential of x. But if you look at the formula, so we can now talk about the integral of the this differential. Essentially what it is talking about, it is essentially telling that I am talking about this of 1 into dx. Basically it is talking about a change of y. When f dash x is 1 when it is dx. So, dx is equal to 1 into dx. So, basically it is talking about that I find a function whose derivative is f x. So, 1 into dx. So, find a whose derivative is basically 1 in this case. So, that is why this symbolism of integral of dx, it actually means you are integrating of a function. So, this function f dash x is the derivative of f of x here. If you look at this point, this function f dash x is the derivative of f. So, f when you take the derivative it becomes f dash x. So, similarly here also this is this function whatever, if I write even integral f x dx. So, essentially what? It is integral of f dash x dx, because f is the derivative of capital F, and then this is nothing but del of f, and this is actually your f, your antiderivative. See, everything is linked by this very simple formula that a very small change in y which takes place when there is a very small change in x, because the function is continuous. Please remember that, because every differentiable function is continuous, and that is nothing but the derivative into the differential of x. So, this essentially means x to the power 0 into dx. So, is x to the power 0 plus 1 by 1. So, it exactly forms into that formula. So, what is the function whose derivative is this. So basically you are actually using this formula. So again this is something I want to repeat. So you are looking at integral fx into dx. Now you have the function f of x plus c, which is your so such that f of x, take the function f of x plus c, and now you have that f dash of x is equal to fx. So this is antiderivative of f, this is antiderivative. Now what happens here? Let us, this is a very important thing. Now I can put, instead of fx I can put f dash x. Right, and this is nothing but by this formula integral of df, and integral of df means again breaking the parts and bringing it in. So it is again f plus c. So that's all about it, and that's the whole game. So please remember that. Again you can also use this formula. So it's again the link between the differential of y and differential of x, and that is giving you this simple formula. This is the formula that you do in antiderivative. It is again all linked with the Taylor's theorem, and Taylor's theorem has its root in the binomial theorem. I would like you to think, why do we write 1 by x dx is equal to ln mod x plus c? I am sure many of you really won't realize it if I just ask you. So I request my TS, I will request my TS to put an explanation to this as a PDF file in your forum, so that you get some understanding of it. We have very less time now, 3 minutes to go. So what we are going to talk about is something called substitution. Means how do you for example use some other function and make your function look simpler, right. For example, what is the first method that you learn in integration apart from calculating and this antiderivatives is substitution. And that means the following, that okay, take an example, I will just give you an example. So say you want to integrate 2t cos t square dt. Now what you want to do, you want to simplify this into a form where you can immediately apply the antiderivative. So now suppose I take u is equal to t square, this would immediately imply by that the differential of u is nothing but the derivative of t, the differential of y is equal to f of x. So u is equal to f of t, the derivative of t, which is 2t into the differential of t. So you see of 2t dt. So what was t square here? T square was u. So this becomes integral cos u du, which is nothing but sin u plus c. Now you put back u is equal to t square, so it will give you back sin t square plus c. So what is the general process of this whole thing, right? So I will just come back to this slide where I have made a mistake. I had put an h square here, which I have now removed. The error term I had made a mistake is just it is h squared by 2 into f double dash c. There is no h square here, I just made a mistake while writing. So this is the basic substitution method. The step do is basically what you do. So basically if you suppose you have integral of v dash, v is a function of u dv, sorry v dash of u, but you are writing in terms of, you are integrating in terms of u. So v is a function of u and you are taking its derivative, that can be written as v dash u of x into u dash x dx. Basically you are replacing u is equal to some function of x, u of x, and then this u is equal to u dash x, or du dx is equal to u dash x. So du is equal to u dash x dx. So u you are writing as a function of x. So v is a function of u and you want to integrate v dash u of du, but now you, because u is a function of x, you are writing, replacing u as a function of x, and now you are putting the whole integration in terms of function of x. So u as a function of x, so d of u, the differential of u, as we have just learned, is the derivative of u into the differential of x, and this is exactly what you get. This is exactly what you get. Okay. Now some more example. Okay. Now if you want to even look at what is the meaning of this in terms of substitution, that is f of ux u dash x dx, this is a substitution, basically the same substitution law. It is nothing but f of this, because u dash into dx is basically du. So, f of ub minus f of ua. So, you may not remember this algebra etc., because substitution is something you would very much use. For example, substitution is something you would very much use. For example, if you take integral u into root 2u minus 3 du. So, what should you use? What should be the function that you should substitute? So, what should be the relation between v and u, because v was a function of u. So, v I should choose here as 2u minus 3. So, u would be equal to half of v minus 3. So, basically du would be equal to half of dv. So, you will replace du with half of dv, you will replace this with v and u with that. So, basically you will have, so this integral will now become half of v minus 3 v half dv. So, now it is very simple, because now it is just integral of half of, that integral of f plus g, integral of f plus g of dx is same as integral f of dx is addition of the integrals, integrating the sum of two functions. This is a very simple known formula. So, I am not repeating such things at this slightly higher level. So, here you know what to do. So, half of will become 1/4. So, it will become v to the power 3 by 2 dv minus integral 3 v to the power half dv, and you know how to write down the answer, which I leave to you. Following for the case where you really want to use substitution method and do definite integral, let us take an example. For example, minus log base e log 2 to 0 e to the power x root over 1 minus e to the power 2x dx, and let us see what happens here. And I will tell you which book I am telling all this from just as I finish it. So, so let us try ux is equal to e to the power x. So, if you find this, then du is e to the power x dx, very good. So, what does this whole thing becomes? No, so when x is minus log of 2, so basically what does it become? So, it becomes u of minus log of 2, because now we have to also change these 2 points, right, because you have to understand the following fact, that now I am changing over from x to u. So, now this end points has to be also in terms of u. So, this is nothing but half, and e to the power 0 is 1. So, basically this integral will become half to 1 d of u root over 1 minus u square, and we know what is it? It is sin inverse x, which is the antiderivative, plus c is not required, because you can cancel out the c from both the cases. So, and by fundamental theorem of calculus, now this is half and 1. So, what it is? So, you will have sin inverse 1 minus sin inverse half. So, sin inverse 1 is pi by 4, 45 degrees, and sin inverse half is pi by 6, 30 degrees, and so this is nothing but pi by 12, and that is a neat simple answer. And tomorrow we will talk about integration by parts. So, I have given these little examples, you must be thinking that I am joking. Is from a book called I have already mentioned, A Cartoon Guide to Calculus. Okay, I have not spoken about the differential from this book, of course, that is just what I said, but the examples that I have taken is essentially from the Cartoon Guide to Calculus, and this little 2-3 examples that I have taken, and it is a serious book, though you might think that it is a cartoon, so it will be just a joke, but I would suggest every engineer, every economist, any scientist should have keep this book on their desk. They will enjoy calculus and they will start loving mathematics and they will start loving calculus. Available on Flipkart or Amazon, which we use more than bookstores nowadays. If I am, yeah. So don't worry, Larry Gonick is not a joker, he is a Harvard trained mathematician. Thank you very much.